वेलकम टू बिटू नेट कोड चैनल। गाइज आज के सेशन में हम डिस्कस करेंगे स्पैनिंग ट्री प्रोटोकॉल। राइट, दिस इज अ लेयर 2 प्रोटोकॉल दैट वी यूज टू avoid loops in the network. So as per Wikipedia, the definition of a spanning tree protocol is it's a network protocol that builds a loop-free logical topology for Ethernet networks. The basic function of STP is to prevent bridging loops and broadcasts that result from them. Spanning tree also allows network design to include backup links, provide fault tolerance if an active link fails. Guys, what happens that let me go to packet tracer and show you over there. So what we do, we normally connect switches to each other in a redundant way so as to maintain availability, right? For example, these are the access layer switches, switch 0 and switch 1. Okay, we connect end devices to access layer switches and devices like desktops, laptops, printers, servers, and other wireless devices. So the end user devices are connected to access layer switches. Access layer switches are connected to distribution layer switches. So distribution layer switches need to be very fast. So we at distribution layer we can use multi-layer switches that can transfer the traffic very fast. So this layer 2 switching, in layer 2 switching we have to use STP that takes care of any kind of bridging loops. So what is a bridging loop? Let me explain you. As you can see here, all the switch 0 is connected to switch 2 and switch 3. Okay, so in case this one switch fails, switch 2 fails, switch 0 has other path to reach switch 3 or to reach this PC. Similarly, this switch 1 is also connected to two distribution layer switches, switch 2 and switch 3. So in case any of these two switches fail, this PC will still have access to network through other distribution layer switch. And so above the distribution layer switches, we will have core layer switches that are connected to routers or through internet. So this way, in case any of the distribution layer switches fail, user will still have the access to internet. So why do we use a spanning tree protocol, and what will happen if spanning tree protocol is not enabled on our switches? STP is by default enabled. Let me show you that. Show spanning tree. We can see that these are the, let me make it a bit bigger. We can see that right now spanning tree is enabled, and all the ports are in forwarding stage, right? This is the status forwarding, and the role of every port is one is root, other are designated. So we'll discuss all this in detail. So right now spanning tree is enabled. So that is why there is no loop in this network. If I try to ping from this desktop to this, I will be able to reach, right? Because there is no loop in this network. So let's do one thing. Let's do this experiment and disable STP for some time. No spanning tree. VLAN 1. Enter. Okay. Now let's go to other switch. No spanning tree, VLAN 1. Okay, so right now you can see that these three switches are in block mode, these ports. Okay, so let's these ports are blocked by STP so as to avoid loops. No spanning tree, VLAN 1. Okay, now immediately it changed to green. So now disable spanning tree on this fourth switch also. No spanning tree, VLAN 1. Okay, now all are green. So that means all the paths are available. So packets can go from anywhere to anywhere. But what will happen in this type of condition? Let us suppose if I send a if this PC wants to send a packet to this PC. What will happen initially when there is no MAC address entry in MAC table of a PC or ARP table of PC or MAC table of switch, right? In those conditions, they do broadcast to find the MAC address. So ARP request will be generated and then switch will try to find out the MAC address of this PC. So what we are going to do, let's go to simulation here and let's create a packet. Add simple PDU. I put this here and I trying to ping this machine. At this time, this machine does not have MAC address of this. IP address is already configured, right? I have given 10.0.0.1 IP address to the PC1 and 10.0.0.2 IP address to PC3. Now let's see what happens. Let's click on capture then forward. Okay, now frame is created by this PC and let's see what's inside this. We can see that this packet frame is received by fast Ethernet 2-1 this port, okay, on the switch. So this is the MAC address of PC1 because this PC does not know the MAC address of this PC. So that's why it will do broadcast. So that's why in the destination MAC, so it is the broadcast FFF, right? So this is the source MAC, this is the destination MAC, and packet source IP address is 10.0.0.1 and destination IP address is 10.0.0.2 and at this end out layer, okay, it is the same information here. Also we can see that the frame source MAC address does not exist in the MAC table of switch, right? Switch adds a new MAC entry to its table. Now whenever switch gets any frame or any data from any device, okay, it learns the MAC address and notes that MAC address into its MAC table. Okay, so switch has learned the MAC address of this PC. So the frame destination MAC address matches the receiving port MAC address, the broadcast address or multicast address. The device decapsulates the PDU from the Ethernet frame. The frame is an ARP frame. The ARP process processes it. The active VLAN interface is not up. The ARP process ignores the frame. Okay. This is a broadcast frame. The switch sends out the frame to all ports in the same VLAN except the receiving port because the destination MAC address is FFF. So switch will send this frame to all the ports it is connected to, right? So let's see what happens next. Placing packet in strict priority queue. Low queue size exceeded, packet is dropped. The port fast Ethernet 1/1 is sending another frame at this time. The device buffers the frame to be sent later. Okay, now let's see what happens next. So switch, what the switch will do? Switch sent the packet to this switch. Okay, this is the, you can see here, this is the ARP request. It looks like my packet tracer is there is some problem. It is hanging. So let's see now. This switch has sent the packets at both these switches, right? It is connected to switch 1 and switch 2. Okay, so from because this is a ARP request, we can see here. This is a ARP request. So and destination address MAC address is not known. It's broadcast going to both the switches. So let's see what inside these packets here. The device takes out the frame from buffer and sends it. Fast Ethernet 01 sends out the frame, right? And Let's study this frame. The device takes out this frame from the buffer and sends it. Fast Ethernet 2/1 sends out the frame. So now let's see what happens next. See, this switch also does not know the MAC address. So this switch and this switch sends the frame to all the ports except the source port, right? So let's study these. We can see that source header MAC address is this and destination is this. Destination is FFFF, right? So let's read the details. The frame source MAC address does not exist in the MAC table of switch. Switch adds a new MAC address entry to its table. So switches are learning the MAC address, source MAC address, right? But because they do not know the destination MAC address, so all the switches are doing broadcast. This switch did the broadcast to all other switches it is connected to. This switch also did the broadcast. This sent to this and to this. Now this switch is getting same source from this path as well as from this path. So switches are in confusion. This is called MAC flapping. Flapping term is used when MAC address, same MAC address is learned from two different paths, right? So let's go next. Okay. So now this switch also doesn't know the destination MAC address, so it's sent to it. This also did the broadcast. So these frames will keep on revolving in this network, and they will never reach the destination. Okay. So let's study this frame. Uh, we can see that source MAC is this, destination is still this, right? And these if we do keep on doing next these switches will always frames will always stay in the network, right? So this is called the loop in the network. This is never ending system, and we can see here that there still our process is going on, right? Our process is still trying to find the MAC address of a destination because switches are confused and they do not know from which path MAC came and where to send it. So let's click on delete. Let's stop this, go back to real time, and now let me show you from here. This is the MAC address of this PC1, right? If I try to ping 10.0.0.2, this ping will never reach because frames are revolving inside the network. Let's try from this PC2. This has IP address 10.0.0.2, ping 10.0.0.1. This also will not work, right? Because our process is not able to reach the destination. Our process is not able to find the destination MAC address. So let's do one thing. Enable spanning tree, right? Switch 0, switch 1. We can see that the port's color has changed. Right now STP process is running and STP is trying to find out is there any loop in the network, and it will block a few ports so that a loop can be stopped. The job of STP is to make sure there is only one path to every device, and the other path is used only when the first path goes down. So enable STP over here also. Now this switch is also learning the ports, MAC addresses, and enable here also. Okay, now all these are in learning. Show spanning tree. Okay, now this is in listening mode. So this is in learning mode. We'll discuss all the modes of a spanning tree in a short while. So the one port is in learning, other is also in learning, one is forwarding. So we can see that still some okay, now most of the ports are green and this port is blocked, right? So let's see if our topology is stable. Now this port has all the this switch has all the ports in forwarding. Let's check this switch. This switch has one root port. Okay, I will discuss what are designated ports, root ports in a short while. Okay, we see all the switches in green, right? That should not happen. Some ports should be some ports should be blocked. So let's see where we did not give the no spanning tree command. Spanning tree protocol is running on switch 3. What about this? Here also this is running. Okay, let's try to ping now. Ping is still not reaching, right? So that means there is a loop in the network because all the ports should not be green. At least few redundant paths should be blocked. Okay guys, now convergence has taken place successfully and STP has blocked a few ports, right? Switch 1 has blocked this path and this switch has blocked this path. Now there is single path to every switch. This switch will let's see which one is the root here. Guys, root bridge is that bridge that has all the ports in designated mode, right? Here the role should be designated, but I see that one port status is still learning. So let's wait for a while. Okay, now all are in forwarding stage. So this bridge is the root, right? So switch 0 is the root. Let's go to switch 1. It has F11 is in blocking stage. This one is blocked, right? So now let's try to ping from one PC. Okay, now ping is reaching successfully. Ping 10.0. Okay, from here also ping is going. Okay, now this is the ARP entry. ARP entry on end devices stays for 300 seconds. And now let's the MAC address table on the switches. Okay, this is switch 1. Switch 1 is learning two MAC addresses from port 01. Port 01, uh, switch 1, we have switch 1 here. Okay, so it is learning two addresses from this port. So let's go to switch 2. Switch 2 has no port blocked. Let's see the spanning tree. Okay, so F01 is the root port. F01 is the root port that is connected to root bridge. Switch 0 is our root bridge. So this was what I wanted to tell you, that why do we need a spanning tree protocol. Now let's get back to the theory part. Spanning tree protocol is a network layer 2 protocol that is required to stop a loop in the redundant network, right? Because we normally connect the switches to more than two switches to make sure we have 100% availability at all the times. In case one switch goes down, we should have network availability, right? So now we will discuss how this spanning tree protocol works, and what are these port states, path cost, and what is this root bridge and bridge id, root ports, etc. Okay, so now let's get back to MS Paint and see the first portion that is called root bridge. This is the our first and most important. Let me make the font size 20, right? So first of all, we have a root bridge. Why do we need root bridge? We need a root bridge in spanning tree protocol, because root bridge is the leader of the topology, and root bridge decide which switch will take which path to communicate with the other device, right? Let's make note here. Root bridge takes forwarding decisions to layer 2 topology. Root bridge will decide which port will be in blocking state in STP topology. So this is the responsibility of root bridge to decide which port will go in blocking stage across all the switches, right? Because if there are multiple paths to one switch, one path has to be blocked. Okay, at one time only one path will be used, other will stay in block mode. So this is done by root bridge. Now how do switches will find which switch should be root bridge? Okay, now here we have uh, four switches. This is access layer, this is distribution layer, and above the distribution layer we have core layer that connects to network to internet. Okay, so normally we use multi-layer switches at a distribution layer, and layer 2 switches at access layer. We connect end devices like desktops, servers, printers, and laptops, etc. to access layer switches. And access layer switches do not talk to each other, they connect to each other through the distribution layer switches only, right? This switch cannot directly connect to this other access layer switch. It will connect only through distribution layer. So right now the path is this. Okay, and if this switch goes down, then the path will be through this switch. Okay, now guys, in our network, this switch, access layer switch, became the root bridge, whereas we want that we normally configure distribution layer switches as the root bridges. So we'll discuss how we can do that. Before that, let's go back to spanning tree protocol and discuss some basic terms. Now how switches will decide which switch will become the root bridge. So this, for this thing to decide, there is something called election. Election takes place among switches to decide who will become root bridge. Okay, and this election happens on the basis of uh, two things. First is bridge ID. Okay, and bridge ID is composed of priority and okay. So on the basis of bridge ID, root bridge is elected, and the criteria for this election is low switch with lowest switch with the lowest bridge ID is elected as the root bridge. Okay, now this bridge ID is composed of priority and base MAC address, and this bridge ID is of 8 bytes, out of which 2 bytes are assigned to priority, 2 bytes for priority, and 6 bytes for MAC address. Okay, so this is the criteria for selecting the root bridge. All the switches will send their BPDUs to each other, and they will compare their priority and base MAC address. And the switch that has the lowest MAC address will be selected as the root bridge. Okay, and priority is same for all the switches in the beginning. The default priority is 32768. 32768 by default. And guys, the range of priority that is that can be assigned to every switch can be from 0 to 65535, because we have two bytes for priority, right? 2 bytes means 16 bits, so 16 bit range from 0 to 65535. 0 to 65535. This is the range of priority. Okay, and after that MAC address, and default priority we saw that 32768 for every switch. And switch exchange their bridge IDs with the help of a message that is called BPDU. So every switch will send a BPDU, every switch will generate a BPDU, that is also called bridge protocol data unit. Okay, so when the election takes place, this switch will start generating a BPDU and will send to other switches. This switch will also create a BPDU. This switch also create a BPDU, and so with this switch, all the switches will create BPDUs and share with each other. So they check their priority and MAC address in the BPDU that they receive from the neighboring switches, right? When they see that any switch has a lower priority priority is by default same for all the switches, right? So when they find that MAC address of any switch is lower than my own, okay, then that switch will consider that the switch that has a lower MAC address than me should be the root bridge. So because here this switch 0 had the lowest MAC address, that's why it became a root bridge. Okay, if we want to manipulate this election and we want any other high configuration switch, or according to our network topology, we want that any specific switch should become a root bridge always, we can change its priority. We cannot change the MAC address of switch, but we can change the priority. So lowest priority will always be preferred. So we can change the priority of this switch to lesser than 32768. So let's try to do this now. We want this switch to become the root bridge. Let's go here, show spanning tree. Here we can see that this switch has priority 3276 root ID 32769, that is composed of 32768 default priority, okay, and system ID extension 1 for VLAN 1, and this is the MAC address. So what we can do, we can make this switch as a root bridge. Currently this switch is our root bridge right here, but we want that switch 0 should not be root bridge, switch 1 should be root bridge. So what we will do, we will reduce its priority because the lowest priorities are always preferred. So let's go to switch 1, spanning tree, VLAN 1 priority. Let's see what can be priority. It can be bridge priority in increments of 4096. Either it we cannot make the priority anything. Let's try to make it 1. Okay, we will get the error message that bridge priority must be in increments of 4096. So current priority is 32768. So if we make the priority 4096 less than 32768, let's try to keep it 28672. 28672, right? It accepted the command. Do show spanning tree. Okay, now we can see that this bridge is root now. And let's go to the previous switch. Earlier this switch was the root. Now let's give the command again, show spanning tree. Now this switch is not the root. Okay, so we are able to change the root bridge role by changing the priority of the switch, right? Now different ports are blocked as compared to earlier. Let's get back to MS Paint and note down a few more points. The about BPDUs. Okay, these BPDUs that are exchanged by root bridge. Once the root bridge is elected, they are generated by root bridge every 2 seconds to inform the other switches about the network topology, that all the network switches are in working mode and our topology is stable. And what does this BPDU contain? BPDU contains root bridge ID, sender bridge ID, port ID, okay, path to reach that root bridge, cost, and various timers. Okay, so initially this BPDU is generated by every switch, but after the election only root bridge will generate the uh, BPDUs. Right now let's see what is root port. Root port is the shortest path to reach a root bridge. Shortest to reach a root bridge. Guys, whenever switches connect to each other, okay, and every switch must be connected to root bridge, either directly or indirectly. So the port of every non-root switch that connects to root bridge, okay, is called the root port. Let me show you in Cisco packet tracer. So here our this port is the root bridge. Let me tag it as a root bridge. So root bridge, all the ports of the root bridge should be in designated mode, and the shortest path to reach this switch is called the root port. Okay, so for example, this switch is connected to this root bridge, so this switch of F11 should be the root port. Let's check it out. Okay, we can see here switch 0. Switch 0 has F11 as the root port, right? And all the ports of root bridge, they should be in designated mode. We can see here they are all designated ports. All are in forwarding stage. So root bridge will send BPDUs from all the ports. Let's check show spanning tree for this switch also. This switch has F11 as the root port. Okay, this port is connected directly to root bridge. So this is a root port, and other ports are in this path is in blocking mode. F01 is blocked, okay, and F21 is designated. Now let's discuss how this root port is elected. Root port is elected. Root port is associated with the interface and not carried in BPDUs, right? So these root ports are decided on the basis of root path cost. So guys, what is this root path cost? This is the total cost to reach a root bridge. So this is called the root path cost. So this cost will decide which port will be root port, right? Let me take you to the Wikipedia, and here we can see. Let's check it from here. Root bridge and bridge ID. The root bridge of the spanning tree is the bridge with the smallest bridge ID. Each bridge has a configurable priority number and MAC address. The bridge ID is concatenation of bridge priority and MAC address. For example, the ID of bridge with priority 32768 and MAC address this is the bridge ID will become this priority, and then this one is the MAC address. So this whole part is the bridge ID of a bridge. Default bridge ID is 32768, and it can be changed in multiples of 4096. When comparing two bridge IDs, the priority portions are compared first, and the MAC addresses are compared only if priorities are equal. The switch will be with the lowest priority of all the switches will be the root. If there is a tie, then switch with the lowest priority and lowest MAC address will be the root. For example, if switch A has this MAC and B has 222 MAC, both have priority 32768, then switch A will be selected as the root bridge. We already discussed this, right? Now let's have a look at the path to root bridge, that is called root path cost. The sequence of events to determine the best received BPDU, which is the best path to the root, is lowest root bridge ID determines the root bridge. Lowest cost to the root bridge favors the upstream switch with the lowest cost to the root. Lowest center bridge ID serves as a tiebreaker if multiple upstream switches have a equal cost to route. Lowest center port ID serves as a tiebreaker if a switch has multiple links to a single upstream switch, where bridge ID is equal to priority of 4 bits plus locally assigned system extension ID. This is the 12 bits that are used by VLANs, and then 48 bits used by MAC address. Okay, out of 16 bits, they are divided into priority for 4 bits for priority and 12 bits for VLAN. Now guys, it is very important to check the root port and paths also, so let's read this as well. When multiple paths from bridge are least cost paths, the chosen path uses the neighbor bridge with the lower bridge ID, right? The root port is thus the one connecting to the bridge with the lowest bridge ID. For example, in the figure, if switch 4 were connected to network segment, I think this is the example he's talking about. D is segment D instead of segment F, there would be two paths of a length 2 to the root. One path going through bridge 24 and other through 92. So here this is the root. Okay, because there are two least cost paths, the lower bridge ID would be used as a tiebreaker in the choosing path, which path to use. For example, we have two paths from to reach this route bridge from here. Okay, the switch will be with the lowest bridge ID will be selected. Okay, so bridge ID will be based on the priority and the MAC address. Priority is 32768 by default for all, right? So whichever switch out of these two will be will have lowest MAC address, that will be selected, and path through that switch will be the root port. So now let's see what are designated ports. Designated ports, when the root bridge has more than one port on a single LAN segment, the bridge ID is effectively tied as all root path costs all equal 0. The port on that LAN segment with the lowest port ID becomes the designated port. Guys, in summary, we can assume that designated port is the port from where BPDUs are sent, right? In this picture we can consider that if this is the root bridge, all its ports are designated ports. Okay, in this case, this is the root port. If this is the root port, other port will be either be blocked or it will be designated. Okay, so this is the root, this is designated. So from here, this F11 is root port and F01 has been blocked. Okay, and this port will become designated. So this port will forward the BPDUs that it will receive from root bridge to this switch. Okay, but this switch has blocked this port. Okay, so this port has this is the root port because this is directly connected to root bridge. This is a root port blocked, and this is in designated port. But this is the access layer switch. We can disable BPDUs at this port if we want. We will shortly look at that, how we can do that. Let me write here. There can be two kind of port roles. Two There can be two kind of port role. On any switch, ports will have two kinds of role. Either they will be designated or Let's go back to Wikipedia and discuss about bridge protocol data units. What is inside the BPDUs that are transmitted by root bridge? Uh, the format of BPDU is that it will contain following information: protocol ID, version ID, 2 bytes, 1 bytes, BPDU type. What kind of BPDU is it? It is configuration BPDU or TCN BPDU. TCN BPDU is topology change notification. Whenever there is any change in topology of the network, right? Switches will generate a TCN BPDU that is normally generated by non-root switches, and configuration BPDUs are sent by root bridges always, okay, to all the switches. So this flag is BPDU type is of 1 byte, and flag 1 byte, and after that we have more details what kind of BPDU that is being used in the network: RST, MST or SPT. So we will check about these in coming sessions. So then bridge priority is also used, bridge priority system extension, root bridge MAC address, root path cost, bridge ID and port ID, message age. Okay, because the messages that are sent by bridge ID, root bridge, are for limited time, right? So after certain time those BPDUs become invalid, so that is decided on the basis of message age, okay, and max age. So hello timer is 2 seconds, and then there is forward delay and version of STP in use. And guys, these are the spanning tree protocol standard that are normally used. And I think we did not discuss the port states, so let's have a look at port states also. A switch port can have following states, right? Whenever a switch is turned on, so first of all the switch port will be in blocking state. A port would cause a switching loop if it were active. To prevent the use of loop path, no user data is sent or received over the blocking port. BPDU data is still received in blocking state. A block port may go into forwarding mode if other links in use fail, and spanning tree algorithm determines the port may transition to forwarding stage. Guys, whenever the switch is turned on, first of all the switch port will be in blocking state. After that it will go into listening stage, where the switches processes BPDUs and awaits possible new information that would cause it to return to the blocking stage. If it does not populate the MAC table and does not forward frames at this stage, right? After the listening stage, switch will go into learning stage. While the port does not yet forward frames, it does learn source MAC address from the frames received and adds them to the MAC table. So after a learning state, switch port goes into forwarding state. A port in a normal operation, receiving and forwarding frames. Okay, and then there is a disabled state, that is if a network administrator has manually disabled the port. So these are the 4 port states through which a switch goes through: 1, 2, 3, 4, whenever STP convergence is happening. So guys, these listening and learning, the duration of these states is 15 seconds. Whenever STP is converging, the switch will stay into listening state for 15 seconds and learning state for 15 seconds. Okay, once it determines that there is no loop in the network, right, then switch port will go into forwarding state. Guys, now we are going to discuss another STP version, that is called Pvsd. Let's write down here Pvsd. Pvsd stands for per VLAN spanning tree protocol, right? STP is for one VLAN, that is called VLAN 1. Okay, and that was not sufficient to manage the network, because we always create multiple VLANs in the network. So STP was not sufficient for multiple VLANs, right? So we Cisco decided to create a Pvsd, right? That is used if we have a multiple VLANs, and for every VLAN we have different instance of STP. So this is called Pvsd, per VLAN STP. So let's note a few important points about Pvsd. Pvsd will have per VLAN STP instant, per VLAN for every VLAN. Okay, there will be a different BPDU that will be generated, and it provides loop free topology, GY redundancy, and load balance. Guys, load balancing is not provided by STP, whereas PVST provides us load balancing. And let's note down the next point. In PVST, there will be multiple bridges, right, for every VLAN, multiple route bridges. So there will be more instances of BPDU. In STP, single BPDU will be transmitted across the entire network by a route bridge, and in PVST, because there will be multiple route bridges for multiple VLANs. For example, if there are two VLANs, there will be two route bridges. So those two route bridges will generate two BPDUs, two configuration BPDs for their individual VLANs, right? So let's note this down. Different VLANs will have different route bridges. For example, for two VLANs, there will be two route bridges that will generate two BPDUs for both VLANs. So let's discuss PVST on Eve, right? Let's go to Eve, and this is the Eve I have configured on my machine. And let's create a new lab. Add new lab, PVST lab. Okay, let's save it and add objects. We will add Cisco switches. Let's add layer 2 switches and give them a prefix SW and change their icon, and let's keep it 2. So we are going to use here, let's create 4 switches, right? We will create two access port switches and two distribution switches. S1 and S2 will be distribution layer, and S3 and S4 will be access layer switches. So let's add the node. Uh, let's add virtual PCs. We will add 4 virtual PCs, and we will create two VLANs. Virtual PC 5, 6 here, 7, 8 here. So we will put this VPC 5 and VPC 7 in VLAN 1 and VPC 6 and 8 in VLAN 2, right? Now let's connect to switches. And these access port switches never connect to each other. They always communicate through a distribution layer. So these are the redundant paths. Let's connect this switch also to both the distribution layer switches, and then these the distribution layer switches should also be connected to each other, right? And we will create VLAN 10 over here and 20 on 6 and 8. So let's select all the nodes and start selected, and let's take the console access. We can see that currently the topology switches have just started, so their status is listening mode. This switch has converged. Its ports are in forwarding status. Only one is in blocking. That means this is also not the root bridge, right? Let's go to this one. This has the root port, so that means this is also not the root bridge. Let's see which switch becomes the root bridge. So I assume switch 1 is the root bridge based on the MAC address, because this has the lowest MAC address. Priority is 32768 plus 1 for VLAN, so 32769 for all the switches, right? We can check here, all the switches have same priority, but based on the MAC address, switch 1 is the root bridge. Now this is the access layer switch, and we don't want that this switch should be the uh, let me have a look. Who was the root bridge? Was it? It was switch 1. Okay, switch 1 is the root bridge. That's okay. And switch 2 uh, is the non-root bridge, right? So what we want, that a switch 1 should be enabled, elected as a root bridge always. So what we can do, we can in Pvsd we have a few additional commands provided. We can configure this switch as root primary. So let's see how we can do that. Spanning tree, VLAN 1. Okay, configure switch as root. Now here we can decide which switch should be. We can configure switches as a primary root bridge or secondary root bridge, right? If we have two VLANs, we can configure switch as primary for one VLAN and secondary for another VLAN. So before doing that, let's uh, create VLAN 10, VLAN 20. Okay, so what we will do, uh, let me create VLANs on all the switches. VLAN 10, VLAN 20. Okay, now we have two VLANs on all the switches. What we can do, we can put this PC in VLAN 10 and this in VLAN 20. So we want that for VLAN 10 traffic should go through this switch. Okay, uh, traffic should go this way, and for VLAN 20 traffic should go this way. This will be primary for VLAN 10 and this secondary for VLAN 10 switch 2. Okay, and if this switch goes down, then traffic will go through VLAN traffic will go through switch 2. So that we can do here. Now let's configure spanning tree VLAN 10 root. Okay, 10 for we are on switch 2. No, we have to go on switch 1. Spanning tree VLAN, it should be root for VLAN 10 primary. Okay, if we want we can give diameter also. Let's not go into that, we'll discuss this later on. And for 20 this should be secondary. Okay, and let's configure switch 2 as primary for VLAN 20. And 10 for 10 for VLAN 20 it should be primary and VLAN 10 it should be secondary. Let's go to switch 1, show spanning tree 10 root detail. We are on switch 1. VLAN 10 root. Okay, looks like it is still converging. Now we have created a VLANs on all the switches. Now let's configure these ports as trunks, right? Ports that are connected to other switches. So on switch 3 we will configure E02 and E03 as a trunk port. Similarly to other switches also. Let me create trunk ports. Let's start from switch 1. E0/0 switch port trunk encapsulation. Let's keep the in encapsulation as default, right? Switch port mode trunk. So the by default switch ports are in auto mode. So what we can do, switch port trunk switch port mode dynamic desirable. We will make all the ports as desirable. Okay, so switch 1 port E00 is desirable. Exit interface E- E0/1 dynamic desirable 0/2 dynamic desirable. Okay, for switch Switch 1 all ports are dynamic desirable. So switch 3 ports are auto. So they will automatically make trunk if the other switch is in desirable mode. So we will configure switch 2 also as a desirable. So let's go to switch 2 and go to interface 0/2 switch mode dynamic desirable E0/0 dynamic desirable interface E0/1 desirable. Okay, show interfaces trunk. Now these are the VLANs that are part of all these three ports, right? So now let's see spanning tree VLAN 10 summary. Okay, so here it says root switch 2 is the root bridge. We can see here Pvsd is running on switch 2. Okay, and this is the root bridge for VLAN 10. Okay, and extended system ID is enabled. So spanning tree VLAN 10 root detail. So we can see that guys, one also important thing that I would like to tell you that the priority of the root the switch, okay, that changes by 8192 if we give the primary command, and for secondary keyword the priority changes by 4096. So the for a VLAN 10 we have checked, also check for VLAN 20. So for VLAN 20, it's for VLAN 10. This is not the root, right? This is the root ID 24586. And let's check on switch 1, VLAN 10. Okay, for VLAN 10, switch 1 is the root. Also check for VLAN 20. For 20, this is not the root. For 20, the root ID is 2000. Let's compare with this one. Okay, this is the root bridge for VLAN 20 because we gave primary command. We can compare from here. This switch 2 is the root because we gave primary command here, and for switch 10 this is the secondary root, and switch 1 is the primary for VLAN and secondary for VLAN 20. Let's note it down over here. Using primary keyword, priority reduces by 8192, that is from default 32768 minus 8192. Okay, and for secondary keyword, priority reduces by 4096, that is from the default, right? These keywords work only if the default priority has not been changed. Okay, so this is very important point we have to keep in mind while using the primary and secondary keywords. These keywords don't work if we have already changed the priority to something else, from default to something else. If we have changed the priority to something else and then we want to make any switch as a primary or secondary, in that case we have to change the priority manually. Okay, prime without taking help of primary or secondary keyword. These keywords won't work in that case. And a few more important points about Pvsd. Let me write it here. Pvsd, because this is a Cisco proprietary protocol, so it works only on Cisco switches. In case we have non-Cisco switches in domain, Pvsd will not interact with them as they will run on STP, right? So to resolve this problem, Cisco had enabled Pvsd plus protocol to Pvsd plus was used, right? Now let's get back to spanning tree protocol, and there are few more important features we should discuss. This is the rapid spanning tree protocol. We will discuss this also, but before that, I want to tell you about BPDU guards, root guards, and BPDU filter and loop guards. Right? So let's discuss those also. Let me search for them over here. Before BPDU guard, let's start with the root guard. Let's open the Cisco document. These are the STP protection mechanism, right, that have been uh, developed by Cisco. Okay, so root guard is an STP feature that is enabled on a port by port basis. It prevents a configured port from becoming a root port. Root guard prevents a downstream switch, often misconfigured or rogue, from becoming a root bridge. How this works? Let's go back to our Cisco packet tracer. For example, this is the root bridge, right? This is all its ports are in DP mode. So, for example, anybody inserts a rogue switch over here, okay? Uh, let's put a rogue switch over here, okay? And if anybody tries to connect this switch to this root bridge, and this switch uh, reduces its priority or changes its MAC address, right? So and try to become the root bridge. So this rogue switch can disturb the whole topology of the network. It can bring entire network down. Okay, so to prevent this, to prevent any switch from becoming the root bridge, this root port, this sorry, root guard feature was enabled on the switches. So this feature is enabled on a port by port basis. It prevents a configured port from becoming a root port. So how can we can do that? Let's go to root bridge. Which one is our root bridge? And go to interface. Switch 1 has all interfaces in DP mode, right? So let's go to it interface E root guard is enabled port by port basis, right? So what we can do is spanning tree guard root set guard mode to root guard on interface, right? So if we give this command over here, okay, and any other switch tries to connect, tries to become the BPDU, so this port will be disabled and network topology will not be broken. So let me show you how we can do that. Enter. Okay, now I have enabled root guard on E0 by 0. Okay, now I will try to make switch 3 as the root bridge. Let's connect to switch 3. 0/2. What I will do, I will try to reduce the priority of switch 3. Priority of the root switch 3 is 32769. What I will do, I will try to reduce the priority to less than switch 1. Let's see what was the priority of switch 1. 24586. I will reduce the priority less than 24586. So interface spanning tree, VLAN 1. Let's try to do that for VLAN 10. Port priority, not from here. Let's try to configure for all the VLANs, right? Spanning tree. Let's do for VLAN 10. Spanning tree VLAN 10 root primary. Okay, let's see what happens now. Show spanning tree. Right now STP convergence is happening. Let's see who is the root for VLAN 10. And compare it with switch 3. So we I'm sorry. So we can see that for VLAN 10, switch 3 has become a root, right? And because root port is not visible here, and let's see what is the condition on switch 1. Show VLAN 10 root, right? So switch 1 is it is connected to Ethernet port 2 is root port for switch 1. Let's check the detail include BPDU. Okay, let's debug switch 1. And here we can see that switch 1 is now sending BPDUs, and the switch 3 is receiving BPDUs, right? Switch 3, okay, we are for switch 3 we have to check for 0/2. and for switch 1 we have to check for 0/0 because the root bridge is enabled on per port basis. So guys, whenever we enable root guard on any switch port and if it receives the superior BPDU, that interface should be moved to inconsistent state. Right, so let's check. Let me undebug, stop the debugging on both the switches. Now we will check if the port on which we enabled root guard, whether that has been moved to inconsistent state or not. So we will give the command show spanning tree inconsistent ports, right? So we can see that this port has been moved to root inconsistent because this port is now receiving the superior BPDUs from switch number 3. Okay, now this port is not functioning because this is receiving the BPDUs uh, from switch number 3. Okay, if we check the details of switch 3, it's continuously sending the BPDUs. It will keep on sending the BPDU as long as it is sending the superior BPDUs. Switch 1 will keep its Ethernet 0/0 port on which we enabled a root guard. It will keep that port in root inconsistent state, right? So how we can remove it from root inconsistent state? We have to remove the cause of the problem. So for that we have to change its priority back to uh, default so that it can stop sending the superior BPDUs. So we will move the priority of this switch 3 back to its default. So let's see how we can do that. Spanning tree VLAN, we change it for VLAN 10 for, priority 32768. Okay, VLAN show spanning tree VLAN 10. Now let's see who is the switch. So we can see that it became the root port automatically as soon as we change the priority. Earlier it was not showing its port as a root port. Let me show you over here. Here also we can see that root guard unblock. Root guard had blocked the port and when it received the superior BPDUs. As soon as the switch 3 stopped sending superior BPDUs, root guard unblocked the port on switch 1. Now we can see that now again it has started sending the port. Earlier it was receiving the superior BPDUs, right? Show spanning tree, VLAN 10, root bridge. Okay, now we can see that its root port is not there, so this is the root bridge. Okay, this is the root bridge. Now guys, let's discuss about BPDU guard. Root guard we have discussed. We use root guard to stop getting superior BPDUs, to stop BPDUs from other switches and stop them from becoming root bridge. This is the this was the function of a root guard, and then we have another feature that is called BPDU guard. BPDU guard. Guys, we use BPDU guard in the condition where we enable a port fast feature. Let me show you over here. Let's go to a Cisco packet tracer. Normally access port that are connected to end devices, right? We don't need a trunking on those ports. But what can happen? Any rogue device can remove this PC and can connect a switch to the access port. Okay, and then he can try to send the superior BPDUs, thereby disrupting the STP topology. So we can enable a BPDU guard on the access ports where port fast is enabled. Port fast is the feature that we enable on access ports of access layer switches, so that they do not have to go through all the STP mm, the status is right in into moving from a port from blocking to a forwarding stage. It normally takes 15 seconds for listening, 15 for learning, and then it goes into forwarding stage. So this is a very long time. To reduce this time, we enable port fast feature on the access layer switches, so that as soon as the end devices is switched on, immediately a port can come into forwarding stage. So we enable port fast feature and BPDU guard on the access port switches um, access ports. So let me show you over here how we can do that. Let's go to switch 3. We can use a command spanning tree. We enable BPDU guard along with the port fast feature spanning tree. Let's see, we have a port fast feature spanning tree port fast. Okay, and along with that we can enable BPDU guard. We normally enable BPDU guard only on those ports where BPDUs are not expected. So we don't expect a BPDU from an end device. Okay, if anybody will try to connect a switch from this port, only then BPDUs will come. So to stop that, we can enable BPDU guard where we have already enabled port fast. We can see here enable a port fast BPDU guard on this switch, right? So if we give it into the global mode, it will be enabled for all the ports where port fast feature is enabled, right? So let's make it default, enter. Otherwise, the second way of enabling BPDU guard is to go into uh, let's go have a look from here. Ethernet 0/0. Other way of enabling spanning tree guard, no, spanning tree port fast. For interface mode, we have BPDU guard here directly from in the first. Don't accept BPDUs on this interface, right? So we can enable spanning tree BPDU guard. Okay, and enable this command we can use in interface mode. If we want to enable BPDU guard in default, then we can give in global mode. So this is how we can enable BPDU guard on the access port switches with access layer switches with the access ports enabled, right? So guys, this was the detailed tutorial on spanning tree, and I hope you like this video. In case you have any questions or anything you did not understand, please let me know in the comment section, and we will discuss that in the coming sessions. Thank you for watching this video.